Welcome back. In this section, we are going to discuss about autoencoders and its application to anomaly detection using a real-world data set. The complete section of the experiments in relation to real-world data sets can be found in section 5. But here, I would like to introduce you to a couple of data sets, give a brief introduction to it, and see how we can use autoencoders to detect anomalies. Let's get started with the. Let me just take you to a couple of slides to give a brief description of the data set which will be used in the experiments. So we are focusing on using autoencoders, and I have also implemented the one-class support vector machine in order to compare the performance of the autoencoder with the one-class support vector machines in detecting anomalies. The data set of interest here is the Sydney Harbour Bridge data, wherein over 800 joints are monitored. In this case, for the sake of the experiment, we are considering only 2 joints as shown in the figure. So one is a healthy joint and one is a joint with known damage. And there are about 3 sensors being placed, which captures the accelerometer and the excitations of any vehicle going over the lane. And the data is collected at 375 hertz for about 1.6 seconds. And as previously described, there is a damage in one location which is previously known. I would also like to talk to you briefly about this bookshelf, which is a lab-based structure data set, wherein you can explore yourself in the hands-on section and see how the experiments are set up and how autoencoder and one-class SVM behaves on this data set as well. So I will leave this exercise to you as a hands-on exercise, wherein I will take you through the code implementation for the Sydney Harbour Bridge data using autoencoders in this section. The bookshelf lab-based structure is a very interesting structure which we can find real-world applications in scaffolding structures which are used in the civil buildings. So we could use to determine the health of the joints and the stiffness of the bookshelf or the scaffolding structures, and so that any loosening of the joints would not render the structure weak. So for the lab-based structures considered, we have a 3-storied structure as shown in the figure. So each story has about 8 sensors. So in total we have about 24 sensors, and the excitations of the sensors are measured in the pairs across each and every corner, and the data set is collected and made available for experiments. So I do have a section for the experiment for you to explore yourself. So having known the background about the data set, let us hop on to the Google Collaboratory environment. I hope that you have followed along the video for setting up the Google environment setup in order to run these experiments. If not, I encourage you to go and look at the video which helps you to set up the Google environment to run this experiment, the Google Colab environment to run this experiment. So and we are using TensorFlow 1.x versions for all our experiments in this tutorial. So once you have loaded the environment and executed this cell would load the necessary source code and the notebooks related to the experiments. And moving on, so in this cell we have shown the implementation of a simple autoencoder. It's an autoencoder with one hidden layer and having a latent encoding dimensions of one encoded dimension, one embedded layer, and we are using the mean square error as the loss function, using Adam as the optimizer. So let us go and see how the experiment is structured. So firstly, we load the FFT features of the data, and here we do have identified the the anomalous samples, and with the known joint having a damage, and we are being provided with the labels, and accordingly we fetch the training and the test set following n number of trials. So yeah, you can run for n trials to ensure the robustness of the implementation of the code, as well as in order to validate the performance of the algorithms for various trials and runs. For each and every trials and runs, you can change, you can have different permutations of the train and the test set. So we are following the standardization or the data normalization is an optional step, but if you wish to do the normalization, you can follow it and see how the performance changes. So it could be a good exercise for you to change the scalar or incorporate the scalar and see how the experiment performance varies. So as far as one class SVM is concerned, since we are provided with we assume the experiments are conducted in a one class setting, wherein only the healthy data, we assume that only healthy data is available, and the damages are not known in prior. So hence we formulate the problem while using the one class SVM. We only use the healthy samples, and then we predict the labels and compute the F1, the balance accuracy, and the AUC for the one class SVM. And as far as the autoencoder is concerned, we are having, as previously described, we are having a simple model of autoencoder with the mean squared error as the loss function, and Adam optimizer using for optimization as an optimization algorithm. So in here we pass the trained data set in order to train the autoencoder, and once the autoencoder is trained, we predict the reconstructed images and compute the mean square error. As a threshold, we consider we set the threshold to be mean plus 3 times the standard deviation of the mean square of the mean square error what we obtain for the training data set, and accordingly we assign the labels for the test data. So herein we compute the values of the F1, balance accuracy, and the AUC for the autoencoder based approach as well. So we could see the convergence plots in case of autoencoder while using training and test data set, and this plots show you the decision boundary obtained by using both one class SVM as well as deep autoencoder. I strongly encourage you to play around with the code and see how changing the standardization scaling using standardization for normalization affects the performance. Well, as extended hands-on experiment, you could as well work with the bookshelf data, which I explained, and this could be quite an interesting way how the data set is prepared. And similarly, you can execute both the one class SVM as well as the autoencoder to verify the performance of these algorithms on this bookshelf data set. I hope this introduction would help you to get your hands-on with the code and start experimenting with your own data set. And I'll be around for any queries or questions. So have fun. Thank you.